Hello and welcome to Engineer's Mindset. So in this video, I'm going to show you how to determine the reactions and the supports of such a beam or any beam that looks like this. Now in the previous video, I took time to explain different kinds of supports and loads we have while analyzing sharp and bending moments. Okay, so do well to take a look at the sharp and bending moment playlist to get everything clearly. Okay, so I said in that video that whenever you see a diagram like this is called a pin support, while this is called a roller. So if you see these bulbs under, it is called a roller, while these loads are called point loads. So we are now going to find what the reactions are the supports A and B on D. What are the supports? A and B are actually what the supports. Alright, so the next thing to do is what to outline the free body diagram. That's the first thing to do. So you bring back the beam. So I said that for a piece of board, we have two reactions. One of the reactions is vertical, and the other reaction is horizontal for a piece of board. So this is point A, and the vertical reaction we simply call it R A Y, while horizontal support we simply call it R A S. So R stands for reaction. A simply means at point A, so reaction at point A. Y denotes vertical, while X denotes horizontal. Okay, so at point B, we have another force, a point load of 5 kilonewtons at point B. At point C, we also have a point load of 10 kilonewtons. Meanwhile, at point D, we have a roller, and I said a roller always has a reaction that is normal to the surface. Okay, but for horizontal beams, rollers are just usually on a vertical reaction. So you simply have R, D, Y. So this is point D. Okay, but the reaction is always normal at 90 degrees to the surface. Alright, so you have this. Now, the first step you do, this is now the free body diagram. You have removed the pin support and you have detected the forces that act on the pin. While for the roller, it's just one force normal to the surface. Now, the first thing to do after this is simply what? Carry out your equilibrium equation. The equilibrium equation is actually two, but I'm going to use one in this class. Okay? The first method is simply what? Summation of the entire work from static equilibrium law. Okay? So from static equilibrium law, you simply have that summation of the entire force acting on the x-axis is actually what? 0. That's static equilibrium law. It also states that summation of the entire force acting on the y-axis is also what? 0. So that is static equilibrium law. Okay, so if we employ this law now, summation f of x equal to 0. That simply means that add all the forces acting on the x-axis and equate it to 0. So if we take a look at the beam, the only force on the x-axis is simply what? RAS. This is the only force that acts horizontally or on the x-axis. So that simply implies that RAX is equal to 0. So that is the first thing you do. Okay, so employing static equilibrium equation. So the sum of all the forces in the x-axis was 0. So RAX becomes 0. The next equilibrium law says summation of vertical forces, summation f of y is equal to 0. So you simply have summation f of y equals 0. But when doing this, you consider vertically upward force as positive and then vertically downward force as negative. So all forces pointing upwards positive, meanwhile all forces pointing downwards should be taken as negative. Now at point A, we have RAY and this force points upwards, so this force is actually positive. So you simply have RAY. At point B, we have a 5 kilonewtons force acting downwards, so this becomes negative. So you simply have minus 5. Okay? At point C, you have a 10 kilonewtons force acting downwards, so it's negative. So you simply have minus 10. And then finally at point G, we have RDY pointing upwards, so it's positive. So you simply have plus RDY. So these are all the solutions of all the vertical forces on the beam. There is no other vertical force on the beam. So after that, from the equilibrium law, summation of all the vertical force equals 0. So you simply equate this to what? 0. So you have this. So this simply means now that RAY minus minus 15 plus r dy is actually equal to 0. Now let's send minus 15 over to this side of the equation. If minus sign plus an equal to sign, it becomes positive. So we are simply going to have that r ay plus r dy is now equal to 15 kilonewtons. So call this equation 1. Okay, now in equation 1, we realize that we have what? Two unknowns in one equation, which is highly impossible for us to solve for any of the unknowns. So the next thing to do at this point is to take moment. Alright, so we take moment. Take moment of forces at A. Now, the reason why we take moment at point A is this. Take moment about the points where you have what? Numerous of forces. Whenever you're taking moment, because from equilibrium law, the moment about any point is 0. So we are simply going to state that here, summation of the moment about point A is simply what? Equal to 0. So we assume clockwise moment to be positive and then anti-clockwise moment to be negative. Now, this simply means that the moment of the forces acting at point A becomes what? 0. Because moment is force times distance. And at point A, if we are taking moment at point A, there is no distance between RAY and point A. There is also no distance between RAX and point A. So therefore, since moment is force times distance, it means now that this is going to be RAY times 0. Because distance between RAY and point A is what? 0. They are all at point A. There is no distance between them. So that is why the moment of those two forces at point becomes 0. So whenever you're taking moment, take moment about the point where you have numerous of forces, so that the effect of those forces at that point becomes what? Nullified. It becomes 0. So that's why we take moment at point A. So we are simply saying, let every force that takes moment about clockwise direction of point A be positive, and then anti-clockwise moment be what? Negative. So we stand. Knowing fully well now that moment of these forces at point A is 0, we have to move on to the next force. Remember that distance apart, we are 2 meters apart, 2 meters, 2 meters, and 2 meters. Now this force actually points downwards, and I want to take moment of this force about point A. It means this force will go all the way from this direction, because moment is only effect to point A. So it actually means what? This direction, and it's clockwise toward our direction of moment. So it means the moment of that force is positive. It's clockwise our direction of moment, so the moment of this force is positive, and moment is simply force times distance it takes to get to point A. So the force is 5 kilonewtons. Distance it takes this force to get to point A is simply what? 2 meters. So we simply have 5 times 2. Also, the 10 kilonewtons force is also acting downwards. The moment of this force about point A will also go what? In this direction. So which is actually like this, which is also what? Clockwise moment. It will go all the way from this direction to get to point A. So it is clockwise and it's positive from our direction of moment. Okay, so distance it takes this force to get to point A is simply what? 2 plus 2, which is 4 meters. So the moment is now force times total distance it takes this force to get to what? Point A. So we simply have plus 10 into 4. Okay, and then finally the force we have left on the beam is what? RDY. And RDY is pointing upward, so it will go all the way to this direction to take moment about point A. So look at the direction of moment now is against our direction of moment anti-clockwise. So it's negative. Okay. So therefore, distance to take this force, first of all, to get to point A simply was 2 plus 2 plus, which is 6 meters. That's the diagonal of beam. So it becomes minus the force, which is R dy times distance, that's 6. That's equal to 0. So if you have this now, 5 times 2 is 10, plus 10 times 4 is 40, minus 6 times R dy gives us 6 R dy, and that's equal to 0. Of course, 10 plus 40 gives us 50, minus 6 R dy is equal to 0. So we can now simply send minus 6 R dy over to the side of the equation. Negative sign plus an equal to sign becomes positive. So we simply have that 50 is equal to 6 R dy. So we simply make R dy subject simply by dividing both sides by what? The coefficient of R dy, which is 6. So divide both sides of the equation by 6. So I will simply have the RDY is now 50 divided by 6. So that simply implies that RDY is equal to simply 8.3 kilonewtons. So the reaction at point B is simply 8.3 kilonewtons. So having known the value for RDY, simply substitute RDY into equation 1. RDY into equation 1. So in place of RDY, we simply will put in that value as 8.3 kilonewtons. So we simply have RAY, so that becomes RAY plus, in place of RDY, we have 8.3, that's equal to 15 kilonewtons. So we simply send plus 8.3 over to this side of the equation. Positive sign plus an equal sign becomes negative. So we simply have that RAY is now equal to 15 minus 8.3. Therefore, RAY is now equal to, that's 6.7 kilonewtons. So RAY and RDY are what the reactions at point A and point D. Meanwhile, RAX was given as what? 0. So that is how you find the reactions at those supports. Alright, so in the next video, I will see you with another wonderful question on how to determine reactions at what? Supports. This time around, in the next video, I will talk about UDLs and UVLs. Alright guys, thanks and cheers.